5 times! What? These numbers are insane! I don't think I can pull another one like that out of my arm. Behold, the Frametime improvements. Okay, bear in mind, this implementation doesn't contain lights or shadows yet. I have a feeling both of those will just devastate Frametime once implemented. So take this with a grain of salt, would you? For completeness sake, this comparison is to the original logic VoxelHex did in the past and not the fine-tuned version I also proposed in part 1. That logic, in a nutshell, is requesting missing data whenever encountered during ray iteration while tracing the scene. To improve on this, what I did was basically restricting data requests to a few times per second. Resulted in less friction as the common request buffer was used way less. Here's also a freeway Frametime comparison just so you have the complete picture. Now that that's out of the way, let's dive into how can you do this in your own engine. If you watched my previous video, you already know why this is better. You know, be proud, good job, go outside. Let me reiterate. And although this method is pretty neat, I think it delegates responsibilities incorrectly. Rendering shouldn't be losing frame time for data selection, because rendering and data selection is kind of a different responsibility. The race conditions generated by the data requests and the overhead for updating usage information quite significant. Most problems the visibility-based approach solves can be resolved with a little bit of elbow grease. And elbow grease it was. Let me show you the mean and lean latest greatest state of the ministry technology that I've been struggling with for the last 2 months. Chunks. Seamless subsets of data, in this case voxel data, which makes it possible to separate a gigantic assembly of information into manageable parts. I currently use nodes and chunks interchangeably, except chunks in this context usually refer to some kind of spatial organization of matrices, whereas nodes are recursive data structures containing either one or more matrices or other nodes. My open source voxel ray tracing engine stores data within a tree structure, which is a directed acyclic tree graph, so streaming is based on nodes. Coupled with its MIP implementation, which is basically a level of detail solution, data selection can be controlled very precisely, and it is possible to render only a preview of nodes and by extension the whole tree itself. This whole arrangement makes it possible to have the best of both worlds by using a granular node-based approach within trees and having some kind of other, preferably sparse spatial structure for a larger collection of trees. Or so I think so, because I haven't implemented multi-object rendering yet, but we're going there, I guess. But anyway, to select the data you want to display using a viewport is your best bet. So it's basically trapping the viewer into a cube which follows it everywhere, loading nodes and bricks within its range and unloading whatever is outside. Think of it like your own little pointy bubble. For those of you who don't know, voxel bricks are basically matrices of voxels in my library. There are some interesting questions popping up here. Spoiler alert, bottom line will be more often than not balance. What do you do if the viewport is outside of the data boundaries? Now, an obvious solution here would be clamping, but if the viewer is far away, uploading every voxel brick in a faraway area is A, taking up space needed for other objects the viewer is actually closer to, and B, useless, because the viewer can't see the detail these units actually represent. Thank God MIPs are here to save the day. Every node contains a matrix of voxels, which represent the simplified representation of said node. Since nodes facilitate a recursive data structure, data itself is stored and can be previewed on every level of detail. So, thanks to this, it is very possible to set the resolution for each area by setting the depth wherein nodes are being uploaded to the GPU. For faraway areas, that's a shallow upload chain, and for closer areas, data is rendered in full detail. This also means, by the way, that nodes are uploaded even from beyond the viewport, but only above a certain depth within the tree hierarchy. This makes it possible to upload very little detail of objects very far away. How can data appear continuous even when some data is missing still? You might think since data is always uploaded, this problem is only for a few frames, right? But this issue is not exclusive to this situation. I'll dive in data invalidation and unloading logic later, but for now, let's just imagine that there is an area streamed up to the GPU in its full glory, and then the viewer moves away. Why? Viewer moves onward to explore new areas, and that means some nearby space is promptly going to be overwritten with new data, and you'll have some holes in them, while some data will remain because there is enough space on the GPU still. These holes are very noticeable, and it's not a good solution to just erase left behind areas completely, as the viewer can turn back anytime. The data just erased would be uploaded again. In this situation, any data left inside the GPU is a very valuable thing to have because you don't want to upload something and then unload it and then upload again. What is a good solution then? Thank God MIPs are here to save the day. The data at lower detail is seamlessly aligned to the data on higher resolutions. That's what the tree structure is implicitly enforcing. If you ever wondered why this library has those spooky size requirements for the base tree, well, this is exactly why. When looking to override bricks to make space for new data, MIPs are the last bricks to be removed from any given node, because should there be any other missing bricks within the node itself, the lower resolution data can be displayed instead. How do you decide what buffer sizes you need? Theoretically, this method uses a lot of VRAM. I just couldn't accept that my library gobbles up this much memory. Working with GPUs, you do have to set the buffer sizes before you can use them, and they're not that dynamic. Thank God MIPs are here to save the day. Not this time, bro. Lucky for us, the worst case almost never happens. I couldn't even imagine what formation that would even take. So what I did is I divided the space used for the bricks by 4. Alright, this ain't the full story, don't worry. Once the buffers are full, all of the stats on the data requirements are available, so it is possible to allocate a new and bigger buffer and copy the current data there.
Yeah, well, I'm gonna go build my own
buffer
with blackjack and...
Doing this is unnoticeable, really. This makes it possible to reserve the minimum amount of data and handle higher data demands as well, but only when it's absolutely needed. Balance. Phew, that might have been a lot of info. It certainly was a lot to talk about. Let's take a moment to refresh our minds. Okay, break's over. Onwards to data selection. Whenever there's a big enough viewer movement, the library scans the whole tree starting from the root node to find the exact nodes to display within the viewport. It does that by measuring the distance of the node to the viewer. This list isn't the primary force deciding when these nodes are uploaded though, because there are some other factors in play. For example, if a node is surrounded on all sides with full nodes, in other words it's fully occluded, it's not going to be uploaded to the GPU ever. The unloading logic is more or less the same as described in the previous video, where there's a pointer scanning the buffers checking for unused data, which in this case means data that's outside of the viewing distance. The difference here is in the conditions. Instead of taking notes if a certain part of the data was rendered or not, data is being unloaded on basis of proximity. So what library is complete without editing? Displaying edits take priority over the regular upload processes because obviously it's best to be responsive, so uploading nodes and bricks only resume when the modified data is updated. The drawback to this is that if the viewer is moving rapidly while also updating the tree, the data close to them might not be displayed in full detail until editing stops. Also, the viewport does not limit editing, but every update is uploaded instantly to the GPU, in which case even far away nodes and bricks will be uploaded regardless of proximity. If you update a single voxel, that updates not only the brick, but the leaf node containing the brick, and the parent of the node, and the parent of that node, and the parent of that node, and the parent of that node, and the parent, potentially every parent up until the root node. Instead of checking if the update actually modified the node, every node is simply uploaded within the update chain. Lastly, I would like to talk about surface voxels, because in theory the restriction is awesome. You exclude voxels not on the surface area because voxels not on the surface are not going to be seen, not going to collide. Useless! Restricting data to surface voxels is not really possible with my library though. If you have at least one voxel in a brick, then the whole brick is going up the stream. So in order to make use of this, bricks have to be small enough to benefit. And while smaller bricks indeed decrease data size a whopping 90%, it makes the tree so deep and complex that iterating it is just that much less performant. Not to mention the increased occlusion data the library needs to manage, additionally to everything already used. And I do believe occlusion bits should have the same expectations as occupied bits, which is to help and find an early exit at the first possible opportunity within rendering. Because of this, I implemented occlusion bits for nodes instead, because that could better help achieving an early exit during ray iteration. But to be honest, I couldn't measure any benefit. Could that be because of my solution? Who knows? Oh, maybe you. Yeah, help me out, bruh. Tell me what you think. Comment this, challenge this, write with a messenger pigeon, I don't care. Just prove me wrong. I'm looking forward to it. I'd love to see any insight you might have. And we're done. That's roughly what I had to say about streaming voxel data. Well, for now. If you are still here, wow, thank you. I am eternally grateful for your attention. I know this is an amazingly deep and dry topic, just like your mom. You sticking around means that whatever I'm doing here actually gathers interest, and I'm not gonna lie, that feels amazing. It's an honor, really. So I hope to see you next time, except this doesn't work like that, so but I hope you'll see me next time then. Haha.